Assalamu alaikum. Good evening, everyone, and welcome to our webinar NMR Petrophysics from fundamentals to reservoir applications. It's Ahmed from Reservoir Solutions. It's my pleasure to be with you today. Our speaker for this session is Dr. Mahmoud Youssef, a senior geoscientist with more than 15 years of experience in the oil and gas industry, covering both exploration and production across multiple regions. He holds a BSc in geology, a master's degree, and a PhD. Dr. Mahmoud has contributed to major projects in Egypt, Saudi Arabia, Sudan, and Algeria, working with international and joint venture companies. Before we move forward, would like to highlight that all webinar attendees will receive an exclusive $10 discount on our full course starting on July 17. Finally, during the last 15 minutes of the session, we will share the attendance form. Please make sure to fill it out to receive your webinar certificate. And now, without further delay, I'll hand it over to Dr. Mahmoud. Dr. Mahmoud, the floor is yours.
Thank you for your engineer Ahmed for your introduction. Hello everyone and welcome to today's webinar on NMR Petrophysics. Thank you all for your joining us today. Our webinar will not take much more time, just 1 hour, 1 hour and a half. This is maximum time we need. We will pass through slides. After that, if you have any question, please dump it in the chat of the Zoom. And finally, we will take 10 minutes to 15 minutes just for discussion all the question and answer it or everything about the question you have. Let me first share my screen. It's clear now? Okay, let's start. Nuclear magnetic resonance become one of the most powerful technology of the formation evaluation. It's rather than the conventional one. This is more advanced tool used for special advanced measurements that the previous conventional tool cannot detect it. During this webinar, we will begin with the fundamental of physics behind NMR, explore how NMR measurements are acquired, the interpretation, and finally applied on real reservoir characterization, permeability estimation, fluid typing, and carbonate reservoir evaluation. Whether you are a geologist or petrophysicist, reservoir engineer, or student, I hope this session provides practical insights that you apply in your daily work. So let's begin our webinar. The first commercial NMR, let's start with the history of the NMR, how they start. The first commercial NMR logging appeared in late 1960. Initially, they provide only basic porosity measurement, very basic tools, required very slow logging speed. Maybe for 100 feet, you need at least a lot of hours. You need to run this with a very low speed. Over time, the technology is improved with a higher technology until we reach faster acquisition, deeper investigation, better analysis. The old one is just primary tool evaluation or just measurement. During time, during the improvement of the NMR, we can detect now advanced more than 1 to 2, 3 porosity, fluid identification, real-time application while drilling as well. Today, NMR can estimate porosity, permeability, pore size distribution, fluid mobility, hydrocarbon viscosity, and even assisted in geosteering. Okay, let's begin. What is the NMR? NMR, it's depending on hydrogen atom contain single proton. That proton behaves like thin spinning magnet. Normally, this microscopic magnet point on random direction. It will take each one take a direction different than the other one. However, when the NMR logging tool generate strong magnetic field, many of these hydrogen nuclei become aligned with a one direction. This is there is no field of magnet. This is after applied the magnet. It takes the same and sharing the same direction, the same as this example. Once we apply radio frequency pulse, the aligned proton distributed from their equilibrium position. As they return to the original state, they emit measurable electromagnetic signal. This is what we called after that T1 and T2. This signal contains valuable information about the fluid occupying the pore spaces on your reservoir. The rotating motion of hydrogen nuclei occur at a very specific frequency. It's we called Larmor frequency. It's the equation of the estimation derived from this one. Actually, the frequency depends on two things: the strength of the magnetic field, the gyromagnetic ratio of the hydrogen. This is the spine from the reading of the NMR. So let's go for NMR measurement cycle. There is just a complete cycle for NMR measurement. Initially, there is no magnetization. Before we start, zero magnetization. After that, as the long tool move opposite the formation, strong magnetic field cause hydrogen nuclei to align at the same direction as we discussed in the previous slide. After sufficient waiting time, the tool emits radio frequency pulse that rotates the aligned spine. The nuclei then begin to lose synchronization, producing what we call transverse relaxation. Just take care about the nomination or definition of each one of this. Actually, on the final of the webinar, I will give you just a definition slide for each one we will use, inshallah, in the NMR interpretation and processing. Instead of measuring only one signal, the tool repeatedly generated echoes using GPMG sequence. It's carries porcelain maybe gel. These echoes gradually decay over time. The rate of this decay forms the foundation of almost every NMR interpretation, including the pore size, distribution, permeability, estimation of fluid type. Why we should use NMR instead of conventional logs? Already we have conventional logs. This is already measured the porosity, measured permeability, measured the petrophysical parameter of our formation and evaluation. Why I should use NMR, and what is the NMR difference between this conventional tool? This is a case study.
Claro, muito. Uma foto, mano, pau. Eu sou um policia dead, be dead. E eu fui sempre, ele prospectus, why? Never seen why.
Sorry, the sound is very loud. If you have a question, Mr. Roland, please dump it in the chat and I will answer it. Don't worry. Okay, let's continue. This is two example for sand, the same reservoir. NMR becomes such important technology Notice that both rock sample have nearly identical porosity. This is 20 porosity and this is almost 20 porosity. It's sharing the same porosity. If they relied only on conventional porosity log, we would assume this rock have similar reservoir quality because it's sharing the same porosity. But actually, this is not the case. It's totally different during the production of each one of two reservoirs. However, the permeability differ almost 2 orders of magnitude. Why we should see this? If we say sharing the same porosity but different permeability. Because permeability depends not only on the amount of pore spaces, but also on pore size and connectivity. And this is the conventional tool can it measure this one. The only tool that can catch this category or this permeability is the NMR tool. Capture this information through relaxation time. When we apply magnitude, magnetic field, after that we dump it, then we can T1, T2. In this case, we can determine the permeability of each one. Large connected pores produce longer relaxation time. As the relaxation time increases, the pore spaces will be longer and will be larger, and generally higher permeability as well. The same like case number 2. Small isolated pore produce shorter relaxation time and poor permeability. This is exactly the case of number 1. This ability to distinguish pore structure is one of the greatest advantages of the NMR. Also, this is the shape of the relaxation time in case of 7.5 millidarcy permeability, and this is the case of increasing the permeability at the level. So they're sharing the same porosity, but actually totally different permeability. Actually, when we going to reservoir engineer just to perforate this type of zone, if we have the same porosity, they take a porosity saturation. If you don't have the information of the permeability, they will shock when during the perforation of this reservoir. If you have the information before perforated this zone, so we will start with the type number 2, not type number 1. So the decision will save money and save cost and save also your well. Okay, from nuclear magnetic resonance phenomena, it's nuclei absorbed and emit energy, as we discussed before, the presence of the magnetic field. So from this methodology, we can estimate porosity, permeability, pore spaces distribution, also the size of your pores, larger pore or small pores due to the relaxation time, reservoir quality, and the hydrocarbon quality as well, because it's measured the fluid presence of this one. This is the major case we can, I don't know if I added in this webinar, but maybe it's removed due to the time. We can differentiate the heavy oil and the light oil using the NMR. We will discuss it based on the relaxation time, inshallah, during our workshop. So what is the principle of NMR? So the quantity measured are signal amplitude and decay. Actually, small pores, as we said, shorter relaxation time, clay bound, large pore, it's meaning large relaxation time, it's rapidly diffuse the fluid. Here, this is the solid, this is an example. Actually, for this is for T1 and T2, and this is for the decay. If you found that on the bound water, you can found short bound water, short T2, T1, and short T2. For the movable water, it's medium large, long, and this is a medium decay. For the heavy oil, this is short, and T1 is short, decay is slow. For the light oil, this is long T1, long T2, medium decay. For the gas, it is longer than the other one. For T1, T2 is short. It is depending on the D and field gratic G dependent. For the decay, it is very fast. So from our estimation of the NMR, we can differentiate between solid, capillary bound, movable water, the type of oil, heavy oil or light oil, and finally the gases. This is one of the most advanced tool of the NMR. For the conventional log, you can detect this one. The only one you can detect is the core and the RFT, which is not conventional. It has very cost. From the beginning, you can design based on your NMR. It's preferred to be after the triple combo just to get more data, helps you during taking the pressure point, evaluation of your reservoir, and also to can detect the type of oil and if it's maybe the gas, so maybe increase or changing the design of your chips. Okay. For the relaxation time and their distribution, sorry. Okay. Relaxation time and the distribution interpreted to know the permeability Yes, this is now. My sound's clear now. Is there any some issue? Okay, let's see. My sound is clear now. Oh,
Yes.
very good. Very, very good. So let's continue. Okay. This slide introduces one of the most important output of NMR logging, the T2 distribution time. This is the T1 and the T2, which is used mainly on estimation all the parameter we discussed in the previous slides. And instead of giving only one porosity value, NMR can detect porosity according to the pore size. Actually, it is not a lithology dependent. It's not depending on the lithology like the neutron density estimation of the porosity. Think of this graph as a histogram showing where the pore volume exists. This is not measured for it. This is the small pores. The relaxation time is totally different than the capillary bound porosity. It's totally different than the free fluid porosity. Each one of them having three different type of porosity, which we called it CMR free fluid porosity, which is already mainly here. This is the porosity for 3 ms. This is exactly represent the clay, the capillary bound porosity and fluid, and this is the total porosity including three of them. Actually, the NMR can estimate three different types of this porosity. The horizontal axis here represent relaxation time, while the vertical axis represents the amount of porosity associated with each relaxation time. For the total area under the curve corresponding to the total NMR porosity. On the left side of the distribution, we found very short relaxation time representing very small pore that usually contain bound fluids. Toward the right side, relaxation time became longer, indicating large pore capable of producing movable fluid. So as this relaxation time increases this direction, this means long pores, increasing porosity, the capability of presence of hydrocarbon of fluid here. Okay. For the porosity definition, let's examine the different porosity component measured by NMR. The first measurement is the total CMR porosity, representing all hydrocarbon contained on the measured pore spaces. Next is the 3 millisecond porosity, which represent extremely small pores and the clay-bound water. The water is found in clay. Finally, we have free fluid porosity, representing fluid locating in larger interconnected pores that can potentially be produced. This is what we focus on it. The area of this green high relaxation time, which actually representing the good porosity for us for estimation, and the area of the presence of the fluid. The separate of this component, we use a cutoff value, determining this cutoff based on the experience of your field and due to the regional exercise for the NMR itself. Typically, the cutoff is around 33 millisecond for sandstone and approximately 100 millisecond for carbonate. This is the standard range of the NMR Of course, if you have NMR core porosity already from core detecting the NMR, it is more better to use it. If you have a background from your field just to use it, please. It's actually, but if you don't have any information, it is your first time to run the NMR, the range is between 33 milliseconds for the sand, 100 milliseconds for the carbonate. Also, this value should ideally be calibrated using core measurement. If you have, please use it. And we will discuss here how to measure the NMR and how to calibrate it with the core data which already coming from your well. This sample separation allow us to estimate movable and immovable fluid directly from the T2 distribution. From here, I can know the free fluid this only between this 33 millisecond to 30 because it's mainly I know this is sand reservoir. Below this one, this is the capillary bound porosity. I will not depend on it actually because at this time it's not movable hydrocarbon. Maybe it's found hydrocarbon in it, but it's capillary bound as a porosity, so you cannot depend it on your volumetric estimation, especially and evaluation of your petrophysical analysis of your reservoir. For the CMR measurement, let's summarize what information NMR actually deliver. The first output is porosity. This is the most important one. Unlike density or neutron logs, NMR porosity independent of lithology because it's measured hydrogen directly, and this is make it advantage for the neutron density porosity estimation. If you have difference between this reading and the NMR reading, please choose NMR. Finally, in neutron density, it's depending on the cross plot, it's the interpreted porosity. Maybe if you change it, your cutoff for NMR for neutron density from the cross plot, at this case the porosity will change, but here the porosity from the NMR or CMR is measured porosity, not estimated. At this case, it is more reliable, not depending on the lithology. So it's more better and more used for the calculation, especially for the volumetric analysis. The second, the T2 distribution provides the pore size information. As the large pore size, as we mentioned, is T1 and the T2 value will change it. And if I detect a higher large pore, at this case, I would found more porosity, more permeability on your reservoir. The third, the NMR separates free fluid from bound fluid. This is very important because in neutron density calculation of the water saturation, it measures total saturation of your reservoir. But if you're using NMR, now you can differentiate between the free fluid saturation and the clay-bound water saturation. You can detect saturation, you can detect the porosity for each one of them, so you will deliver a good and realistic petrophysical parameter for your reservoir. Finally, when integrated with the conventional logs, NMR assists in fluid identification and reservoir characterization. Not to mention the NMR is advanced tool and is better, so you can't use it alone. No, we can use it for the best calibration tool we used for the NMR is the core data. And if you combine it to the NMR for the conventional logs and the image log exactly, you will find a core-like reservoir that you can take a core from all you can take a core from all your reservoir, but actually using this core together, you can make like core from the NMR and the conventional data through your reservoir to get it more realistic and more good parameter for your reservoir. Okay, there is some NMR issue. You should take it on your consideration. Of course, NMR reading is a very good and it's awesome to use it for your formation evaluation. But at all time, you should take in your consideration some uncertainty present of the NMR or some uncertainty during the logging of the NMR. From the QC of these logs, you should start with the petrophysics to use it because there is some factor affecting the reading during the drilling. Before interpretation in NMR log, quality control is essential. From the logging till we come to the processing center to process the NMR tool. Like every logging tool, NMR measurement can affect it by borehole condition. This is the same like this one. This is here, this is the washout present on the reservoir. One of the first parameter we check is the bad hole flag. Where is the area where the caliper is open? This flag indicates the borehole condition may have degraded data quality. it will highly affecting the CMR or the total porosity here. Like we found that this case, the porosity is not make sense here because due to the high flag. Also the permeability coming from it, it is not the same. There is some check mud surface present on the T2 distribution. You should neglect this zone. You should not estimate on it because this is a bad hole flag. We also compare the measured mud response with expected surface mud properties. You should take it before you run the NMR to calibrate your data to catch this anomaly. If the borehole is enlarged or irregular, the measured signal may include onward contribution from borehole fluid. At this case, you will found wrong T2 distribution time due to the processing. Ignoring this quality indicator can lead to incorrect estimate of porosity and permeability. You will exaggerate your porosity and permeability, and of course, you will affecting on your volumetric estimation. Therefore, always perform quality control before interpretation, from starting the logging acquisition till processing and finally the interpretation. Another factor affecting the NMR is the logging speed. Another important acquisition. NMR measurement required sufficient time for hydrogen nuclei to become fully polarized. So the NMR tool is one of the most slow run you will run on your logging suite during drilling a well. It is you should run. I think the last number I remember it's 0.2 or 0.3 feet per hour or feet per or meter per hour. So it is a very slow tool. Actually, when we run this tool, he told me take the remote control and just switching a movie. If you run just only 200 feet or 300 feet of reservoir interval, we will not run through all your reservoir, of course. You will focus only in the zone of interest because this is very expensive time. It will take much more time because it is low speed. Why we should get low speed for this one? Just to give the proton the time to polarized, fully polarized, because less polarized for this nuclei actually all the result of estimation of the porosity and permeability and the fluid and pore size will be highly affected by this high speed, and finally you will get not the result that represent your reservoir. So this is why manufacturer specific maximum logging speed for different acquisition modes. The note on this slide reminded to never to apply inappropriate real-time speed correction, as they may introduce additional uncertainty into your data. So you will run NMR to help you. Don't run the NMR with a wrong acquisition parameter or wrong design, and finally you will get data misleading you or your interpretation. Proper acquisition is always preferred for correcting poor quality data. This is the insufficient wait time. We also discuss this point. Another one issue, remember the hydrogen nuclei is required more aligned with the magnetic field. This is what we already need. If this waiting period is too short, complete polarization does not occur. The resulting signal amplitude decrease, leading to underestimate the porosity. Information containing heavy oil or large pool, sufficient wait time become even more critical because longitudinal relaxation is slower. This is an example for this one. You need just good speed. You need sufficient time for your analysis. If you need to get proper data interpretation from your NMR. Another one that we should take in our consideration, the bad contact. This slide illustrates one of the most serious problems encountered during the NMR logging. Poor tool contact with borehole well. Actually, this is bad for NMR, should have a pressurized with exceed 80% or 90%, which is more close to your wall to catch the good parameter, because unfortunately the NMR is a very good tool for vertical resolution, but actually the depth of investigation is not high. So if you're not adding the pad very near to your hole, actually you will get no data because most of the tool or half of your tool depth of investigation will read just on the borehole. So all your data will not covered by the NMR. You pay a lot, you stay a lot, you take more time, more for reg, more for analysis, and finally you will get not good data. This is the meaning of the bad contact. Unfortunately, the type of error cannot be corrected during the processing. This is a big mistake, because at this case, we cannot correct this in the processing center. Actually, because there is no connection good with the formation, we will just read on the mud or inside the hole. So it cannot be corrected at all in the processing center. So just take care from the pressure of the bab, take care from your connection of the tool with your formation. Should the formation not have very high washout, because at this case, the NMR investigation should be, at this case, you will lose a lot of investigation, depth of investigation of your tool. The benefits of NMR petrophysics. This is porosity only application. You can use it. It's independent sourceless porosity. This is an example of using the NMR. One of the benefits of the NMR. This light blue color is represent the dolomite, and this is represent the dark blue line is represent the calcite. Quartz is in the blue line, and just this clay is a clay. Hydrocarbon is present on red. The water is present at this case. If you found here the density porosity of the line, we differentiate which one of them. First of all, we estimate porosity from density for the limestone, which is already the dark blue one, and we estimate the porosity from the density for the dolomite, which is light blue one. For the CMR porosity, this is the black one is between both of them. Actually, if you found here from the interpretation, for here, if I depending on just on the limestone, this is the high porosity estimated at this interval. The NMR is catch the area of the dolomite. So the reading of the black one is pretty much with the density, with the porosity coming from the density in case of dolomite. And it's far away from the limestone, because as we see from the lithology here, there is no limestone present as this in zone. Complete to the zone number 2, this zone is mainly limestone with some intercalation of dolomite. If we see here, the porosity of the dolomite is found here, the porosity, and the porosity of the limestone is present in the dark one. If you found here, the black porosity coming from the NMR is have a good match with the limestone, especially in the area with at 100% limestone. We found some different here, actually, because this zone exactly is not representing pure 100% limestone. It is just a limestone with some intercalation of the dolomite. So the porosity estimated from the NMR have a good match, and not have a good match with the limestone porosity totally, or the dolomite totally is just between. So as this case, I will depend on the CMR porosity, which is neglecting the effect of the lithology. Here we just density porosity estimated for the limestone and dolomite is highly affected by the lithology present, but in the CMR, it here respects the presence of the dolomite, 100% dolomite. An area here also as well, if you found the area here, it is some intercalation between the limestone and dolomite. It is just between both of them. This is the more accurate. So this is the benefits of the NMR, and it's not depending on the lithology. This is a real case for the using of the CMR porosity instead of density porosity. For this slide, this is the CMR versus conventional core. Actually, using the core data with the NMR is giving you the most proper data for your interpretation. Core analysis has traditionally been considered the most reliable method for measuring porosity. It is better than NMR, better than conventional logs, better than everything. The core data is the core data, the most proper one to estimate porosity and permeability. However, core data are only available over limited interval. This is the problem. I cannot coring all my reservoir. If I have a reservoir 300 feet or 400 feet, 100 meter, I cannot give a core from all this slide, from all this reservoir. Actually, I take just interval in our reservoir. I cannot cover all my reservoir by core. And also it is more expensive and time consuming to acquire. It need a lot of data because you take the core, handling the core, going for the lab. preparing the core ships and started the estimated the density, porosity, helium porosity, total porosity, effective porosity, and permeability, and so on. Making the rock typing, it takes a lot of time. NMR logging complements core analysis by providing continuous measurement along the entire well bore. In this comparison, notice that the NMR-derived porosity closely match with the core measurements. This is here a very good match between the core porosity points, which are coming from the core data, and this is the core porosity coming from NMR, the black one. This is the true one, the CMR free fluid porosity. This is the porosity less. It's only the porosity of the fluid inside my reservoir. Here it is after you remove the effective capillary bound fluid. On core, they didn't remove it, but in NMR they can remove it. This is the difference between the flush this line and the black line. Also, you can calibrate it, the permeability as we found here. This is the black dots is the permeability points coming from the core, and this line is represent the CMR permeability. Actually, it's have a very good match with this data. This is the best tool for calibration of the NMR or CMR using the core data. Okay, NMR in carbonate application. Carbonate reservoir, يعني we're talking about 60% of the world hydrocarbon reserves found in the carbonate. Most of major fields we found in the world, which is huge and highly produced, like RFD in Gulf of Gulf Arabian Gulf, and all this mainly carbonate. All of the huge reservoir present in the world, mainly in carbonate, not in plastic, represent some of the most prolific oil and gas field globally during the world. But the carbonate also most challenging reservoir to characterize due to their highly heterogeneity pore system. Actually, the deposition of the carbonate is totally different than the clastic one. The clastic sand, we know it, the deposition environment. We should know the matrix, we should know the component present in it. It is easy to detect. Also, easy to detect the heterogeneity, less heterogeneity found because it's deposited in the high energetic water and so on. So the clastic is more easy. For the carbonate, no, there is a high heterogeneity pore system found. Complex the genetic can be occurred due to the presence of the secondary porosity, affecting of the fluid, and so on. The genetic history and significant variation in porosity and permeability. We found in some reservoir, like the Barawashif in the Western Desert, an example, we have 400 meter or 400 feet of thickness of it. The highermost part is the highly compacted limestone. There is no reservoir, there is no organic carbon, there is no organic matter. For the lowermost target, just only 200 feet. It's totally different in the deposition, totally different in the porosity, totally different in the TOC estimation, totally different in the reservoir performance and the production as well. Unlike the sandstone reservoir, as we mentioned, porosity permeability generally show good correlation. Carbonate reservoir often poor relation between these properties. So carbonate is one of the most challenge of the NMR formation may possess high porosity but low permeability. This is another case for the carbonate, or low porosity with excellent permeability due to fracture or vugs, which count in the secondary porosity. As we all know, sandstone, the primary porosity is the dominant on it. The secondary porosity is not present mainly in the sandstone. Just only one case of the sand you may have secondary porosity, only one case. But in the carbonates, this is very easy. Can be due to the fracture, can be due to the vag solution, and so on. So maybe you can catch the good porosity for the carbonate, but finally you have a very good permeability during the perforation and the production as well. Molecular magnetic resonance has become essential tool for carbonate reservoir evaluation because it's directly measured hydrogen information about first, which is mandatory in the evaluation of the carbonate. Pore size distribution and the fluid mobility. So it can be have a good permeability or not, which cannot be catched by the conventional tools. Bound and movable fluid. If we found the fluid, if this fluid can be bound or it can be movable for the production. because it's mainly the main issue of the carbonate. Maybe you have a huge amount of hydrocarbon present on your carbonate reservoir, but actually you can get a recovery factor between 2 to 3% only. So more than 90% of your fluid presence on your carbonate, you cannot produce it due to the bound and movable fluid present on your carbonate. And this is one of the most challenging one in carbonate reservoir. You found a very high porosity, found a good porosity as well. The permeability maybe good in some interval due to the carbonate present, but actually the recovery factor from your reservoir is not exceed 2 to 3% due to the presence of the movable and the bound fluid, which cannot be catched by the conventional logs. Through the NMR, you can detect this one and to see what is movable and which is bound. Also, you can detect the permeability, reservoir heterogeneity, fracture, and the vacuum identification. NMR significantly reduces uncertainty associated with the carbonate characterization and improve reservoir development decision for one of the most prolific oil and gas fields reservoir in the world is the carbonate reservoir. One of the most important application of the NMR, why carbonate reservoir are challenging? This is the question. This is an example from well GPT-4. It's probably core zone. Actually, what you found here is the carbonate was different here from the core data and texture on it. Carbonate rock undergo extensive diagenetic process through their geological history, including dissolution. Dissolution, the highly heterogeneity of the pore system. It's unlike the sandstone. It is just a complicated reservoir, and it is very challenging. It's addressed the challenge directly measuring a fluid with the pore system rather than relying on slowly the bulk rock properties. The cementation inside your carbonate, dolomitization, which is here dolomitization meaning the just replace the calcium magnesium of limestone with the magnesium nuclei instead of calcium, which is more small in size. It's increasing the porosity, which we called it dolomitization. You cannot detect this one with the conventional code because he cannot catch this category. Recrystallization of the carbonate, fracturing, which coming from the faults or coming from the high compaction of your reservoir. This process creates extremely complex pore system. Characteristics of the carbonate reservoir: strong heterogeneity, multiple pore type, poor porosity permeability relationship, presence of the fracture and the vugs. You cannot detect it through the conventional log. Significant lateral and vertical variability, complex fluid distribution. So, consequently, the conventional log method alone often fail to fully characterize the carbonate reservoir. This is the most important application of your NMR is to detect those ones. Here, this is the T2 distribution time, and this is the cutoff used. The more, if your transition time data is representing the high in the cutoff, at this case, you have a good reservoir. In case of this area, you have T2 distribution lower, so you will get just a permeability lower. As we see here, this is the water permeability. This is the porosity. The porosity here is decreased. The permeability is decreased due to all your data is below your cutoff. Here, the area is here exceeding the cutoff, which you have a good permeability, good porosity, good reservoir quality inside your reservoir. This is a real example. Here, the top reservoir is very good reservoir. The middle reservoir is a bad reservoir. The lower reservoir is a very good reservoir. At this case, your reservoir is divided into three zones. Each zone have their parameter, have their issues. Here there is no reservoir, but the way it is the same carbonate. All this data is a carbonate, sharing the same texture, by the way. But actually, it is totally different due to the distribution. Only the reservoir is here. The reservoir is here. If you just don't have NMR, you will just let's perforate all this one, and actually you will not gain nothing from this area. You're just increasing the hydrocarbon column of your estimation, measuring the volumetrics of your reservoir, which is completely wrong because you add thickness that is no porosity, no permeability on it. from the conventional log, you cannot detect this one because at all cases for the conventional log, you will found the high resistivity, high porosity due to this compaction. You may be found here resistivity higher. The resistivity is highly affecting the water saturation of your estimation on the formation evaluation. At this case, you will found all this is the reservoir, but on really, this is not all the reservoir. The reservoir only at this zone and only this zone and this big zone. For the T2 distribution here, there is no porosity, there is no permeability. This is a very tight reservoir. It cannot produce nothing. Okay, this is another question. Why in NMR is particularly valuable in carbonate? Why we should use it? Conventional log measured bulk properties and may not adequately describe complex carbonate pore network. This is exactly showing this example as we found here. The conventional log cannot catch this one. NMR directly measured fluid contained inside the pore and they provide information about distribution of pore size, fluid mobility, effective porosity, permeability potential, reservoir connectivity. Here, this is the same reservoir, but there is no connectivity between this reservoir and this one as well. Actually, this reservoir after the perforation, this reservoir is not connected to this one. So actually here in just this area, which not represent just 3 open field 5, 15, 15 to 50. So we're talking about here 30 meter only reservoir. This 30 meter is not connected together. This zone actually as a separator between the reservoir number 1 and the reservoir number 2. As this case, this separates the two reservoir, and this case, this is a reservoir which is separated than this reservoir. So this is reservoir 1 and reservoir 2. Reservoir connectivity is very, very important in your estimation because it's highly affecting your hydrocarbon column. Actually, if I use here the conventional logs, I will take here, this is the reservoir, this is the top reservoir, this is the base of my reservoir. At this case, I'm very good. I will take 30 meter as all. This is my reservoir, and this is completely wrong during the estimation of the volumetrics. Actually, my total reservoir here is the first reservoir I will estimate it on it. It is just 10 or less than 8 meter, and here it is just about 7 to 15, another 8 meters. So the maximum reservoir thickness about for both of the reservoir, it is just around 16 to 15 meter out of 35 meter thickness of the reservoir. So, and also each 8 meter is totally isolated than each other. They are not connected. So this is the one of the advantages of the NMR to estimate the reservoir connectivity. NMR also few logging techniques capable of distinction between the micropores, macropores, vugs, fracture, bound fluid, and movable fluid, which is one of the most challenging in our carbonate reservoir. Let's go for the summary of the CMR NMR application. The first one, lithology independent porosity, so they can directly measure the porosity instead of neutron density or density density porosity calculation, which is depending on the lithology interpretation. You should correct it between the cross plot first, and after that you estimate the porosity. But NMR is a direct porosity tool, independent than the lithology. Free fluid porosity, this is reserve calculation. This is very, very important parameter for your estimation of the reserve because this is the only porosity for the fluid that you can produce from your reservoir. Maybe you have a very high porosity total, which exceeds 30 to 25, but the free fluid porosity, it is just only 10 to 8% of porosity. As this case, when you estimate the volumetric estimation, you will get the free fluid porosity, which is more accurate because if you estimate just neutron density calculation, you will get 25 or 23, 24, just like you estimated from the capillary bound and free fluid. Your reserve estimation will depend on 25, but the actually free fluid is only 10 or 11. This is the actual porosity of your free fluid that you can produce from your reservoir. So this is one of the most important effectiveness of the NMR application. determine the water saturation, it's water cut prediction, permeability identification. By the way, the conventional log, they cannot estimate the permeability. The only tool that can, from the convention, can estimate the permeability is a Stonely from the dipole sonic image or sonic vision. And actually, it's advanced tool as well. And after the processing, depending on the quality of your interpreter and the processing center. But here you can identification exactly from adding the cutoff for the T2 distribution, you can detect the permeability directly. And actually, this is the productability, the permeability that you should use during the production. Pore size distribution, also it can detect the reservoir quality, the fine grain reservoir, thin grain reservoir, large grain reservoir. It's highly affecting the quality of your reservoir. Gas detection, it is very important to detect the gas from the NMR, because in some cases, NMR, if you don't know from the neutron density the presence of the gas, if you depending on the density on estimation, the gas effect will highly affecting your porosity reading. You will estimate porosity higher than the really found for your reservoir. But here, if you detect the gas, so you can correct the gas from the conventional, using the convention and NMR to detect your gas presence on your reservoir. Bitumen identification, plugging, tar sand, which is a high sand, which is a high low API oil for the evaluation and reserve estimation. This is some of the summary of the NMR application, which is actually more advanced tool and so on. What is the source of uncertainty in your NMR interpretation? We have some uncertainty maybe present due to some issues that we mentioned in the previous slide. But how can I interpret this one if they miss during the acquisition or during the logging? It's extremely powerful. No measurement is completely free from uncertainty. The first source is acquisition uncertainty. There is no tool as it's advanced or good tool, but finally it's not, doesn't have any uncertainty. Of course, we will face some uncertainty. Poor logging speed, low signal to noise ratio, or insufficient polarization time can all reduce measurement quality. This is one of the acquisition uncertainty. The second source is the processing uncertainty. Processing uncertainty after you acquisition the tool and go to the processing center. Maybe you have a good acquisition, but the processing is not good. Converting echo data into reliable T2 time distribution. T2, this is interpreted from the processing. You cannot get it from the acquisition data. It's after the processing. It's the equation inside the processing center to get this distribution, which we already added the cutoff for it for your estimation of your reservoir. Required mathematical inversion, which can sometimes amplify noise. If you have noise and you can't catch it, or the processor in your processing center is not qualified enough to do such processing for the NMR, you will get a noise high ratio, and in this case, to the distribution will be not right. Finally, geological uncertainty. There is some geological uncertainty also. We can take it in our consideration after the acquisition and processing. Complex pore system or heterogeneity, like we found in the carbonate, lithologies, and natural fracture may complicate interpretation. If you don't know how to interpret this one, or you don't have the information from the geological itself, it will not help you to take it in consideration during the processing and the interpretation. Recognizing this uncertainty allow us to make better informed reservoir decision. If you neglect all this one and just take it in your consideration to get a better data, at this case, you will end up with a very good analysis of your NMR. What is the limitation of NMR logging? Each tool have a limitation. Finally, it is the logging techniques. Low porosity formation generates weak signal that may reduce interpretation confidence. Also, heavy oil often have extremely short relaxation time, very short, as we mentioned in the previous slide, making fluid typing more challenging. Very tight reservoir contain fluid with limited mobility. resulting in weak NMR response. All this one is affecting the reading of the NMR or the response of the NMR. Complex carbonate reservoir may produce multimodal T2 distribution that require careful interpretation. This is one of the most tricky. A lot of the interpreter can take it into their consideration, and actually they lied in this mistake. And finally, this is the most one challenge of the carbonate. Finally, you should have a good geological knowledge from to choose the interpretation and taking some geological to decrease the geological uncertainty, especially in these cases or especially in the complex reservoir system. Finally, the environment conditions such as temperature, mud properties, and the borehole geometry can also affect the measurement quality, as we mentioned. If you have a high washout, the sophistication of the tool is not high. So at this case, you will end up with a very long interpretation, and final result will not be represent your reservoir reading. Understanding this limitation help to avoid over-interpreting this data. If you get this uncertainty or the limitation before you run the tool, maybe if your decision, I will not take any gain from the NMR, I will run it. This is also a conclusion. Finally, you should know how to use the tool, how to perform the acquisition program, how to perform the processing program, how to perform the interpretation program. Is the NMR tool will help me on my reservoir or not? Maybe it's not helping. So the decisions, I will not run for it. So you should know all of this data before you design the NMR, just to get the best benefits from using it, because actually it's an expensive tool, taking more time, but finally you should take it if you use it and if you can use it or not. This is a decision. Okay, how to manage the NMR uncertainty? How to manage it? Fortunately, many sources of uncertainty can be minimized. This is good. The first step, proper acquisition planning. You should prepare, as we mentioned before, we should have a good acquisition planning. High quality logging condition always produce better interpretation. Secondly, rigorous quality control. Procedure should be performed before any interpretation began. This actually should be done. Third, NMR results should be calibrated using laboratory core measurement whenever available you have. Integration with the conventional logs. This is very important to get. Laboratory measurement, sensitivity analysis. This conventional log, image log, like core analysis, production data, geological understanding, provides the most reliable reservoir characterization. This all approach significant reducing the uncertainty. You should use all your data together, finally, to get the best image for your formation evaluation, finally using the conventional and the advanced logs, advanced image as well. If you use the image with the NMR, you will get a very nice interpretation of your reservoir. Okay, now we discuss the NMR physics, the NMR procedure, how to run it, how to acquisition, how to processing, how to interpret, what is we can get from the interpretation, what actually we can avoid during the acquisition and the processing, how to design it, how to decrease the uncertainty, how to increase the confidence, how to convent with all another logs. Let's take some case studies. I will not take much more time from you, gents. We will go ahead for some case studies. This is a case study of the carbonate reservoir characterization, one of the most challenging reservoir for the NMR. The main problem is the conventional log showing high porosity. High porosity here. This is the value of the fight, but the productivity is very low. We found here high resistivity. By the way, sonic is good. This is mainly carbonate. And finally here, this is a high porosity reading present of 5. NMR result, multimodal T2 distribution. In this case, the porosity is decreasing by more than half. large amount of bound fluid. Not all your fluid of the estimation from your porosity cannot be detected. This is a large difference between free fluid porosity and capillary bound porosity. The capillary bound porosity is very high, and this is the reason why on the conventional lab you cannot differentiate between both of them, free and the bound fluid. But for the NMR, there is a high bound fluid, large amount of bound fluid here in this carbonate, and this is the reason why it's have a good porosity but low productivity. Limited connected pore system. As you found here, this is not connected. It's more or less the same like the example we give it on the carbonate characterization. Interpretation, high porosity with mainly isolated vaggy porosity. This porosity estimated from the neutron density actually is good, and it is right, by the way, but this porosity is not connected because the bound capillary volume is very high and the free fluid is very low. This is the interpretation that's coming from the NMR result. The outcome here, revised reserve estimation and optimized compilation strategy. For this case, the decision is please revise your reserve estimation because the reserve estimation is building on the total effective porosity with capillary bound and the free fluid. And in this case, you should re-estimate your reserve based on the free fluid, which is coming from the NMR reading as this case. We will go for case study number 2. This is the problem is the conventional log suggested poor reservoir quality. There is a bad reservoir quality here. This is another example. We take one example for the carbonate and one example for the tight gas reservoir. By the way, one of the most important application of the NMR you can use it to solve a lot of this problem is a tight gas reservoir. In case of tight gas and tight sand, one of the most important tool you should run in your well is the NMR. The problem is the conventional log suggested poor reservoir quality because, of course, it's a tight, so the porosity will be decreased. NMR, low total porosity, presence of movable fluid. There is fluid can be catched, especially at this zone. Here, this is from the time. There is a good T2 component. The interpretation, there is natural fraction enhanced permeability at this case. And by the way, we mentioned that we have only one case for the sandstone to be have a secondary porosity. Sandstone is always primary porosity. The only case that you found secondary porosity or the fracture in the sandstone, only one, the compacted sand and the tight sand. At this case, the fracture will occur after that because the primary porosity will decrease due to the compaction and due to the presence of the fracture. It is the only case that you can found the sandstone have secondary porosity. But you cannot detect it, of course, with the conventional logs. So the outcome from the NMR interpretation at this case, productive interval were identified and successfully completed. We will not take much more sand for this one. We just only focus on top of this reservoir and this one. This is exactly the zone that we perforated into production instead of all of this zone. This is a good sand, but actually we will just focus in zone of interest based on the interpretation of the NMR. Now we finish just two cases, just two high cases between carbonate and tight gas reservoir. We will go in deep to some worldwide case studies, how they found some problem, and finally how NMR helped them to find a solution for this one. One of the most challenging reservoir for the conventional log analysis is a shaly sand reservoir. This is a real example from shaly sand challenging found in the North Sea, Brent Group, United UK and Norway. This is just here, this is the wells present on the study, and this is the map represents their area. The geological setting is the Middle Jurassic reservoir. The main environment here is the deltaic shore faces, which is a more challenging, especially in the delta here. The issue is a laminated sand shale sequence. For the conventional log, of course, you know, the vertical resolution is not high to catch these changes, and especially in shaly sand reservoir, it will decreasing the porosity, decreasing the permeability, decreasing the reservoir thickness, and finally you will end up with a reservoir from the petrophysics very low quality. The main risk here, underestimated pay due to shale conductivity. The shale is highly affecting on the sand reading, and in this case, the net pay is very low because the presence of the shale sand stratification, at this case, decreasing the porosity, so which will maybe to decreasing your net pay. What is the challenge here? High gamma ray. The high gamma ray reading is present here for the productive sand. The sand characterized by high gamma ray. Actually, in the past, they used the Archie equation. Archie in cherry sand is one of the big mistakes. If you choose it, Archie cannot be run totally in cherry sand reservoir because it will be miss. You will lose your reservoir and you will lose your interpretation. They use the Archie equation. Water saturation overestimated. All this sand was a very low water saturation, symbiotes bay below vertical resolution. Actually, using Archie and Shaley sand model, it is the big mistake you will choose. The better way to estimate the porosity model at this case, uh, using Waxman-Smith or dual water model or Indonesian, just one of them. Waxman-Smith is better here because there is no core data for the calibration. This is benefits of using just Archie. Archie is here is miss. How to solve this issue? The tool uses the basic logs here, gamma ray, density neutron crossplot masked by shale, so that the porosity reading is not good. Deep and shallow resistivity separation. Advanced logs we used here, spectral gamma ray, array induction lateral log, NMR, T2 distribution, free versus bound fluid, resistivity and isotropy, and the image log. This is for the limitation of the thickness of. Just one ask me the question. This is a very intensive logging program, and also it is heavy, and also it's cost money. But each one of them, Gentis, used for a purpose. The first one is spectral gamma ray, just to detect the K therium uranium, just to see what is the shale type on my reservoir. Is this potassium, cerium, uranium? Of course, if we focus on uranium, uranium is less affecting in the porosity and the permeability. If I found uranium, this is better for me or better for my reservoir. Array induction lateral log and RVRH, because for simple reservoir like Shaley sand sequence, the conventional logs cannot detect the ideal thickness because it's range between 1 to 2 feet. If you have one streaks of 0.5, 0.6 from feet, you cannot detect it by the conventional logs. So the resistivity will average all the zone and the maximum of it by the shale. So the resistivity will decrease it dramatically. For this reason, we used RVRH, vertical resistivity and horizontal resistivity. It's better for your identification. Image log, just to say the thin beds, because the image is a high vertical resolution, 0.2 inch, so it cannot detect vertically to detect the limitation of the thickness and sand shale ratio as well from the image, from conductive, resistive, conductive, resistive. The workflow identifies the limitation. Sand from FMI uses RVRH to correct symbed resistivity, just to get the correct resistivity to correct estimate the water saturation. Apply Waxman-Smith or dual water model, calibrated shale volume with spectral gamma ray, validate movable fluid with the NMR, just to see after I done all my workflow. Finally, this reservoir can produce good amount of hydrocarbon or not. I can detect only by using the NMR to see if this fluid can be moved or the capillary bound is very high. At this case, I will not waste my money to just perforate this zone. So the outcome net pay increased by 20 to 35%. We increased the net pay. Several zones previously classified as a water zone proven to be productive and added to production. So this is one of the benefits of using the NMR and the basic of the advanced tool as a whole. So the key teaching here from this point, high gamma ray does not mean non-reservoir in laminated shaley sand. You should depend on the tool that neglect this effect, like the NMR and image log as well. This is a real example. Let's go for a second example. complex carbonate challenge. Also, I take one example for the sandstone and another example for the carbonate. Here, this is geological setting, shallow marine carbonate platform. The rock typing, moldic limestone, boggy dolomite, fracture interval. Here, why this is challenging? Dual triple porosity system. Porosity log gives false confidence. Resistivity not equal to saturation due to the poor complex. Our used here, we're just using density neutron sonic log. Advanced, we used NMR just to make macro and micro porosity. Dipole sonic for mechanical phases, geochemical logs to see the lithology and dramatization. Integration workflow rock typing using the NMR and the image log just to see if all this interval having a homogeneous or heterogeneous reservoir. This is very, very important, this rock timing. Separate the effective for non-effective porosity. Because at a zone of good reservoir with good porosity, I will exclude the non-effective porosity and this zone reservoir. I excluded this from my estimation for the production, identifying fraction control permeability, apply carbonate saturation height model, calibrated with the core data and the production data. The outcome we get from this analysis, high porosity zone, downgraded, non-flowing, low porosity fracture zone upgraded, well placement optimization horizontally. This is the decision and increasing the productivity. So the key teaching here in carbonate porosity alone does not define your reservoir quality. Maybe you can get the quality, the porosity from the conventional log, but using the advanced can help you to define the reservoir quality of your reservoir interval. Finally, this brings us to the end of our today's webinar. We began with fundamental physics of nuclear magnetic resonance, explore how NMR measurements are acquired, and discuss how relaxation time are transformed into valuable reservoir properties. We then examined practical application, including porosity, permeability estimation, fluid typing, carbonate reservoir characterization, some example from carbonate, some example from tight sand, some example from worldwide, uncertainty analysis, and several real-field case studies. I hope today's session has demonstrated why NMR has become one of the most valuable advanced logging technology for modern reservoir evaluation and how it's mandatory, especially in the challenging reservoir. Thank you very much for your attention and the participation. I would now be happy to answer any of your question. I will start with question dumping on the chat. We will just move one by one and answer all your question. And after that, we will open discussion for 10 minutes if you need any other question. Okay. Let's start for our colleague question. Okay. Now it's better. Let's see what is available for us. Is available to stand for what? MS is millisecond, yes. Why is the recording available? I hope so. This is available. It is possible provided presented now. What is the depth of investigation of the NMR tool? It is a low depth of investigation, it depending on the CMR. Actually, it have a good vertical resolution, but low depth of investigation. I think it is less than 1 feet or 0.7. This is the depth of investigation, so it should be the bed pressurized and added to your wall just to get a better analysis and a better reading for it. If your beds, Mr. Hamza, is not connected to your hole, at this case you will lose a lot of your depth of investigation inside the hole. So at this case, you will get nothing from this interpretation at all. What is NMR reading? The effect of gas in NMR reading, as we mentioned, Mr. Ali, it's giving in this slide, the first one. If you mention us here, the gas is highly affecting, increasing the T1 distribution time, and the T2 will be very short. For decay time, this will be very fast. The reason why it can be detected easy the gas presence. As we know, NMR is related to hydrogen, and the gas lower hydrogen index, HI. This is another story. We will discuss it not right now. Maybe during the workshop we can discuss it in detail. This is totally different of using the hydrogen for each one of them. One, since NMR expensive, which are the cases where we definitely needed NMR survey. Yes, this is expensive tool. In which cases I should use, should measure besides NMR. In case of not all your reservoir, maybe you need NMR. If you have six antibodies, like we faced as example, like on the Gulf of Suez example, this is an example, or in the Red Sea, or in the carbonate, some carbonates in the Arabian Gulf. At this case, you have a very thick reservoir body. At all cases, it's produced very well. At this case, I will not use NMR. Just the conventional will be very good for me. But if you have some challenging in my reservoir, like we discussed in detail, Mr. Adam here, tight gas reservoir or tight sandstone or just carbonate, which have a high heterogeneity, good porosity, but there is no production, like the cases we already discussed in our webinar. At all this case, I need NMR. Of course, it's expensive, but it will help me to get a better interpretation, like the reserve estimation. We repeat it again for some reservoir, and also maybe it's decreasing your reserve, like the case number one in carbonate, or you can increase also your reserve estimation, like the case we found on our cases here, on the Arabian Gulf. It's increasing between 20 to 35% of your net pay. So you pay and get your data. Actually, knowing the geological the geology of your reservoir, it's will make you to choose the best practical workflow acquisition you need. In case of shale sand reservoir, the conventional log you cannot depend on it alone because it will be mislead. You need for the shale sand reservoir as example, like if you drill in the Nile Delta, on the Mediterranean, on the Red Sea, or something like that. You need exactly this tool because it will save your cost. Because as you all know, all the drilling on the offshore will be cost money. Cost of the drilling is very high. The one well is exceeded $100 million. So if you run one run with 30 or 50 thousand dollar for the NMR, it's nothing. You save your reservoir and to save the reservoir reserve and production as well. Other logs that you can use combined with the NMR, the conventional log all, core data is the best one for the calibration because if it's calibrated with the NMR. At this case, I use this calibration on the NMR on the wells that they didn't have any core on it because the core data is expensive and it should done in all your reservoir. If I don't found it, it's okay. I can use the parameter of the calibration between core and NMR on the wells that didn't have core on it. Does the light oil affect the NMR? Of course, the light oil and the heavy oil, Mr. Ali, is highly affecting the NMR reading. The light oil is totally different than the heavy oil. The light oil, you will find the T1 is very long and the T2 is very long time. But in case of heavy oil, the T1 and the T2 is very short. You will find the cutoff is very low for it. So they are totally different. And this is one of the most practical benefits of the NMR to detect, or you can predict the hydrocarbon quality of your hydrocarbon present in your reservoir, maybe light oil or heavy oil. This is one of the most benefits of it because it's highly affecting the cost of production and the cost of your facility if you're drilling in exploratory phase. Yes, it can easily detect between the light and heavy oil as well. Yes, Mr. Herod, if you don't have core data, if you have a core data, it is better because it is very good for you for the calibration. But if you don't have core data, it's okay. You depend on the interpretation. Actually, the presence of the core data will help you to detect the real cutoff of the formation. Actually, as I mentioned before, This is an example, 33 millisecond for the sand, 100 millisecond for the carbonate. This is from the regional studies done from many wells, many reservoir, many fields around the world. So they agreed finally after all this data, the range of the sand between 33, the depth, the range of the carbonate is 100. This is what we exactly done. This is not haphazard information. This information is coming from the another wells in another fields, just going for it and for interpretation. And finally, we depend in case if you don't have any core. But if you have a core data and the core data it's saying from this interpretations the cutoff should be 25 for the SAM. Of course, you will get 25. You will not get 33 at this case because now I have data on my hand really calibrated from my well. This is the reason I will choose it and I justify my interpretation. So at this case, I will add cutoff for 25 or 35 as example in case of SAM. The core data tell me that. At this case, I will choose the core data. But if you don't found, you can use the NMR as is. At all cases, it's always better than the conventional log. Okay. So, Mr. Ahmed say we can solve the non-archie due to shale effect using money model like dual water or else, but after all, it's need calibration and here NMR comes. Yes, agree with you, Mr. Mahmoud. Archie is beautiful for always for shelly sand reservoir. Using it is not good. Of course, using dual water and Waxman Smith is good for estimated the real porosity and the water saturation. It's good calibrated. But finally, if you use it instead of using the cutoff from NMR, of course, it will be better. Spectral gamma ray, it's advanced or not advanced tool. Of course, it is all tool, but the interpretation you can get from the spectral gamma ray is better for you for your interpretation, and it is better than the gamma ray, especially for the shale volume calculation. And also, you can get a good information before the calculation, the percentage of the sodium, uranium, potassium on your reservoir. In case of uranium, as I mentioned before, it's not highly affecting the porosity and the permeability. As this case, I will go for it. For the cerium, no, this is now a very high shale content. It will highly affecting the porosity and the permeability. Also, with this spectral gamma ray, I need to see if this shale present on my reservoir is a structure shale or laminated shale or dispersed shale. For case of the structure and laminated, it will not highly affecting the porosity, but in case of dispersed, at this case, your reservoir will produce very low productivity. How to use NMR to identify hydrocarbon masked behind high water saturation zone. This is Mr. Wahidos. I think it is we discuss this case, and also we added for the one on case studies that we have on the worldwide today. Actually, using the normal resistivity tool that we perforate in the well, we found that the water saturation is very low. After we run the NMR, re-estimated the water saturation. The water saturation here is increased by 30% as a minimum. At this case, you increase the increase the hydrocarbon saturation. Now you increase the porosity, you increase the productivity. With the conventional log, you will dump your reservoir and they will not work on it. Actually, after using this saturation, some of the water saturation we estimated from the NMR, after re-estimation from the NMR processing interpretation, we ended up with increasing the net bay because some of this interval, the water saturation is below the cutoff. But after running the NMR and re-estimate the petrophysical parameter, we added this zone to the net bay because the water saturation is enhanced. And so many thanks for you all. Really, many thanks for you. Advanced application. Advanced application. Perfect. Yes, thank you all. Thanks for you. Bad hole, big challenge. So data mitigation. Yes, bad hole is highly affecting on it. You can add a flag, and after that you can remit it in the processing center, adding just from the area of surrounding wells. You can get well at this zone with a good parameter, you will use the parameter of this well to decrease or to remove the effect of this bad hole condition, because the bad hole condition on the T2 distribution and the analysis for the porosity and permeability will increasing the porosity, increasing the permeability. Just the T time distribution at this case will measure it, the fluid you already entering for your drilling fluid. If it's oil-based mud, you will found the case as we showing here. If we're showing here, you will found just a high CO2. This is mainly mud, especially if it have a oil-based mud, you will found something that's not reliable with your data. Okay, let's go for another question. Our colleague John. Is correct, shell volume. T2 cutoff or unconventional source essentially because we tend to expose the hydraulic creating a pressure. This is right? Yes. Right. Is anyone applicable for unconventional? Yes, NMR is a highly applicable on unconventional reservoir, of course. I think I didn't add a slide for this webinar for unconventional reservoir, but I think during the workshop I added more slide for the unconventional, how we detect it, how we estimate it, how to detect if you have unconventional reservoir or not. But I didn't have any slide for this webinar. Maybe during the workshop, it's not maybe during the workshop, I already added slide for the unconventional reservoir. Okay. Means to have multiple. Hello, this is in case usually reservoir with poor petrophysics characteristic. When we run NMR, they give us good permeability. But when we run formation pressure test, we found that is tight. Okay. In some cases, usually the reservoir with a poor petrophysics and low petrophysical characterization. This is a good question, by the way, by Mr. Abdu. When we run NMR, they give us a good permeability, but when we run formation pressure, I think this reservoir is carbonate, Mr. Abdu, right? Because you will find this issue, I think, on only carbonate or very tight sand. And on very tight sand, I didn't expect good permeability. So I think this is carbonate, right or not? In case of carbonate, didn't depend on formation pressure, because formation pressure is depending on your beds. If the NMR showing you a good permeability, now you catch a good permeability. NMR RFT at this case is depending on the probe suction time, and actually they estimate the total permeability or VAG present on your carbonate. And you can get, if your hole not matches the presence of the fracture of your carbonate, now you will always, the RFT will be tight. Actually, more than 50% of the RFT recorded in the carbonate always will be tight if you have porosity and if you have permeability. Of course, yani finally, more than 50% or 60% of the RFT reading will be tight. So I think your reservoir is carbonate. You didn't mention it's carbonate or not, but I think it's carbonate. And this is normal. If you have a good NMR permeability and porosity, go ahead and perforate this zone. Yes, from the T2 distribution, you can getting the type of your fluid, and also from T2 distribution, you can define the pore size is large or small due to the distribution and the cutoff. It's very easy, and we will discuss Mr. Nasruddin. Thanks for you all. Is any other question? If it's not carbonate, Mr. Abdo, it's the sandstone reservoir. At this case, this is a tight sand. Of course, in case of tight sand, you will RFT will not reading at all in case of sand, by the way. It will not read but the conventional log will not catch the secondary porosity on this sand. At this case, the conventional log will say it is poor reservoir quality. RFT will say tight, but the NMR will showing a good porosity and good permeability. The other reason, and by the way, I exclude this reason, maybe in the interpretation on the processing center, there is a problem on the processing of the NMR itself to detect the permeability, because it's not measured not measured before the tool. It should be processing first. And I exclude this zone because, of course, you're working with either Schlumberger or Halliburton. They are very expertise guys, and I think they like in this situation. Actually, in the tight sand, it's very normal. In case of tight gas sand, I showing you in this presentation, the RFT we take more than 11 or 12 points of the RFT. None of them were reading. All of them is tight. And this is normal because the reservoir is tight, and I know this tight reservoir. The probe cannot reaching inside the formation, and cannot, because the RFT is just a probe entering the formation through the porosity and permeability found on it, and sucking fluid from the reservoir to just adding the CC and the building pressure. In case of low permeability, you will always show no reading for the RFT. You sense the missing the beginning. Oh, if you're missing the beginning of the presentation, I think our representative engineer Ahmed in Reservoir Solution will adding the video. I think on by the way, just to see from the beginning. How we can get them parameter from NMR core.
Hello.
Yes, hello. So now all this question.
I am Abdu. I just ask you about question when we have some cases in sandstone reservoir, the NMR give us good permeability, and when we ran formation tester like MDT, we found that it's tight.
Yes,
Why? What?
normal.
I don't understand why the reason.
Yes, this is normal, Mr. Abdo. Why? I think I answered this question, but I will answer it again. For case of sand reservoir, this sand is tight because the petrophysical analysis from the conventional log saying this is a low petrophysical parameter, and they are right because it's a tight sand. On the tight sand, always the RFT will not reading, because RFT, MDT, and so on will not reading, because the in case of tight reservoir, MDT and RFT is depending on the permeability and the porosity found. If you're entering the probe and you should need a high permeability to just suck the fluid from your reservoir and build the pressure up on the bottle of the MDT and close, then apply pressure to build this pressure to see the fluid if you suck from your you suck from reservoir. Actually, in case of tight sand, at this case, you will not get nothing because the permeability is low, and you need more time just to get this sample to not to be tight for the RFT. You should stay on the point at least 1 hour or 2 hour due to this permeability of the tightness of your reservoir is depend on it. Maybe in some interval to just to get this point, you need at least 3 hours. You will not stay all this time just before to get a good sample. We will not stay all this time because it is wasting our time, and maybe your pads, because MTT or RFT is the pads and the probe enters the formation pad very close to the formation. If you stay a long time, maybe this pad, which is rubber, stuck to the formation, and after that the MDT tool is the best tool to stuck during the acquisition, because it is tool very easy to stuck due to the differential or due to the waiting time on the point. At this case, all the points should be tight because you stay between 10 to 15 minutes, and after that you remove to another point. Of course, on 10 minutes or just 30 minutes as a maximum you can get from your reservoir, it's not it's not enough CC coming from your reservoir just to close and build up your pressure. At this case, all your point will be either tight or supercharged. The pressure will be very high because at this case, the pressure will be the sucking fluid is in your fluid will be more or less near to the fluid on used in the drilling fluid. At this case, you will be very near to the pre-job pressure. In this case, will be supercharged. So in case of tight reservoir, forget about the MDT. If your NMR showing you a good permeability, going to say it because if it's the sandstone is fracture, you should to get a fluid from this fracture. You should drilling on the direction of this fracture just to be open for you to enter the probe and drop the formation and drop the fluid in your bottle. If your drilling is not in the same direction of the fracture or far from it, at this case you will found nothing. It will be always tight. So if the NMR showing you this is a good permeability, just perforate this one and just showing you where is my recommendation for you is not depending on the NMR at this reservoir exactly. Run image log before the NMR. Run image first, and after that run the NMR. At all these cases, if you found porosity or a permeability on the tight sand, of course it's fracture. At this case, the best tool you can detect the fracture from it is the image. He can give you the fracture intensity, fracture direction, and also he can showing you the direction of the stresses inside your sand. And it is better for designing the well that hit this fracture in the good position. At this case, you can good production from this reservoir. This is my interpretation.
But
Though
Mr. Mah- but
there is another interpretation, but for me, I neglect this reason. Maybe in the processing or the because the permeability is coming after processing of the NMR. At this case, maybe the processing center you work on it or you work in home is making some mistakes during the estimation or extracting the process and the permeability for your reservoir. This is another story, but
but,
for me, I didn't recommend this scenario.
but thanks, Mr. Mahmoud. But in our case, we ran before imaging, but we don't find any fracture. There is no fracture. But when we ask the service company, a specialist service company, they uh, they uh, they said that NMR don't work in the tight, don't work good in the tight reservoir. That's why they give wrong the permeability.
So as this case, they didn't take into consideration the processing parameter. If the image showing you there is no fracture of this sand, so what is the source of the permeability in MR measurement? So in this case, the processing center making a mistake. Yeah, for me, I just neglect this reason because, of course, he asking you and stay with you during the processing to ask about the geology of your reservoir. Because if you do like that with because of course you run the NMR with the conventional logs with the same company. If they have the same company, should combine it together the conventional with the NMR just to QC the result. If you have some issue during the acquisition, he didn't take it in her consideration. So as this case, he make a wrong interpretation of the NMR. Maybe this is the reason, but for me, I exclude this reason because the working in this fields, the big companies, and of course they have a big expertise, guys. I think they didn't make this mistake. But if the aim is showing you there is no fracture, and this is a second deposit for the sandstone, at this case, I can say it, I can say it very wisely. Actually, the NMR interpretation is wrong.
Thanks, Mr. Mahmoud. Thanks.
Yes. Okay. Is there any other question from our colleagues attending this webinar? يعني thank you all. Thanks for Reservoir Solution to give us this opportunity for this webinar. Thanks for discussion. Thanks for the discussion and the question. Thank you all. See you inshallah on another webinar and another technical session inshallah. Thank you all.